Good evening, everyone. Welcome to MAPS. Welcome to our third MAPS presentation of the semester, the rise and fall of the Sierra Nevada glaciers. So I'm really excited that people can be here. Remember that one of the great things about attending these talks live is that you can post questions in the chat. So don't forget to do that and post comments and questions so that we can have our helpers, Bill Anelli and Susan Kerr, help us with that at the end of the talk. Just a couple things before we get started. I wanted to remind you that we do have one more MAPS talk this semester next month, Friday, April 22nd. It's going to be Dr. Marina Elliott, and the talk is Homo naledi in the Rising Star Cave. So it's about the excavation of the Rising Star Cave. This was one of the 6 underground astronauts who helped to excavate that cave. So that should be another interesting talk coming up. Also, our Great Valley Museum has a really excellent exhibit. If you haven't checked it out, Sayaka Gans's Reclaimed Creations, that's only going to be around another couple of weeks till the end of April as well. And also at the end of April, we have that weekend, Friday the 22nd of April and Saturday the 23rd of April, then the Great Valley Museum will be celebrating Earth Day with free admission and some activities there. So keep your eyes open for that. And next Friday, a week from tonight, is our April Science Night, the first night of the month. The first Friday of the month, we have our Science Night at the museum. So the museum will be open from 7 to 10. And the telescopes will probably start a little bit later than that because it stays light out kind of late. So maybe 7:30 or 8, we're planning to have telescopes on the roof. So those are our cool activities that are coming up. And now I'd like to turn it over to Liz McInnes to introduce our speaker.
Hi, good evening, everybody. Thanks for joining us. I'm Liz McInnes. I teach biology here at MJC. And tonight we have Dr. Greg Stock. He's the first ever park geologist at Yosemite National Park. And he earned his BS degree in geology from Humboldt State University, a Ph.D. from the University of California, Santa Cruz, and completed postdoctoral research at the University of Michigan before starting work in Yosemite in 2006. He has authored or co-authored more than 50 publications on Sierra Nevada geology, ranging from highly technical articles on rockfalls and mountain uplift to the non-technical book, Geology Underfoot in Yosemite National Park. Greg is a professional geologist in California and was recently elected a fellow of the Geological Society of America. He lives in Yosemite Valley with his wife and daughter. And I hope you all will join me welcoming Greg. Thank you for being here tonight.
Thank you. It's my pleasure to be here. And thanks for everyone for attending. I'm going to be talking tonight about glaciers in the Sierra Nevada, touching briefly on the Sierra Nevada's long, interesting history of glaciation over millions of years, but mostly focusing on the state of glaciers in the mountain range today. And because I'm based in Yosemite National Park and have done most of my research here, I'll be talking specifically about the glaciers in Yosemite. So this is probably a familiar landscape to you. This is a photograph of Yosemite Valley. It looked very similar to this today out in Yosemite. And this is obviously an iconic landscape that millions of people visit every year. Whether they know it or not, they are coming to see scenery that is fundamentally shaped by glaciers, right? The U-shaped valley of Yosemite, the steep cliffs, the hanging waterfalls. These are all function of glacial erosion that occurred over millions of years, and it's why this is such a famous national park. If you go up into the high country of Yosemite, you'll see views like this. This is from Olmsted Point off the Tioga Road. The bedrock there, the granitic bedrock, has been scoured and polished by glaciers moving over that landscape. And as the climate warms at the end of a glaciation and the ice retreats back, it will drop the stones that it's been carrying. These are called erratics, and there are lots of these lovely boulders scattered throughout the Yosemite high country. And all of these are evidence for Yosemite's glacial history. And these images are showing on the left, a friend, an artist's depiction of the glacier that was in Yosemite Valley about 20,000 years ago during the last glacial maximum, which was the last time that there were large glaciers on planet Earth. And locally in the Sierra Nevada, we call that the Tioga glaciation. So this is when there was ice coming from the crest of the Sierra Nevada, flowing across really big ice fields in places like Tuolumne Meadows, where the ice was up to 2,000 feet thick. And that ice was flowing over the landscape, funneling down into the existing canyons, filling up Yosemite Valley and the Tuolumne River Canyon. The map on the right is a map that we published a couple of years ago showing the full extent of glaciers in and around Yosemite during that last glacial maximum, or Tioga glaciation, again, about 20,000 years ago. And this was just one of dozens of glacial periods over the last few million years, periods when the climate cooled, ice formed in the mountains, flowed down the valleys, and then the climate would warm back up again, the ice would retreat back. And what was happening in Yosemite and the Sierra Nevada was very similar to what was happening in all mountainous regions and high latitude regions around the world during this time, a global advance of glaciers during these cold periods. And if you haven't seen a plot like this, I think it's important that you do. This is a snapshot. Well, it's actually a pretty long record, more than a snapshot. It's 800,000 years of changes in atmospheric carbon dioxide, and that's the orange line on the top, and a proxy for a temperature anomaly. So it's basically a temperature record. And these are coming from extremely deep, long ice cores in Antarctica. So these are really long records of climate change. And what you're seeing in these squiggly lines is the pace of natural climate change on planet Earth going back upwards of 1 million years. So when those lines are in the upper part of their plot, those are warm conditions. And when they're near the lower parts, those are cold conditions. And you can see that over the last 800,000 years, there's been fairly regular cycles of glacier periods and interglacial periods. So Earth's system toggling between warm and cold periods. I could spend a lot of time explaining why this is, but suffice to say this has primarily to do with the way that it's around the sun and how much solar energy it receives from the sun. So these are orbital drivers of natural climate change. And the temperature plots and the CO2 plots in this case are very tightly linked because they're very tight feedbacks that connect them. So for example, when you warm the Earth's surface, you typically tend to liberate carbon dioxide from places where it's been locked up, oceans, permafrost, et cetera. Conversely, if you increase the amount of CO2 in the atmosphere, you can do that through volcanic eruptions, for example. That will cause an increase in the greenhouse effect, the trapping of Earth's radiative heat, and the temperatures will go up. And then there are similar sets of feedbacks that will cause temperatures or carbon dioxide to decrease as well, right? So the important point here that I want to make is that Earth's climate has been changing naturally for several millions of years in this way, switching between glacier and interglacial climates. And that is what's largely responsible for the Yosemite landscape. It's the fact that glaciers advanced, did lots of eroding and sculpting of the granite landscape, and then the climate would warm, they would retreat back. There would be weathering and erosion of the rocks, sort of preparing them to be easily eroded when the climate cooled again and the next glacier advanced, right? So this is an important long-term understanding of natural climate change in Yosemite, and it sort of sets the context for what's happening with glaciers today. Let me just go back real quickly and say, if you look at the very far right side of that plot, you can see the last glacial maximum, the low point about 20,000 years ago, and then a fairly rapid rise around 10,000 years ago to the relatively warm conditions that we've been in on planet Earth since the last 10,000 years, right? That's called the Holocene period. And we've enjoyed a pretty warm, stable climate for the last 10,000 years, under which our civilization has really thrived. But the warming that we are starting to experience because of anthropogenic activities is happening during one of these interglacial or already warm periods. That's another important note. Okay. There's a lot, I think, that we sort of take for granted in our understanding of glaciers, both globally and in the Sierra Nevada. And it's important to point out that it wasn't all that long ago, a century and a half ago, maybe, that there was quite a bit of debate about whether glaciers were ever in the Sierra Nevada, not just in the past, but if they're present there at all. And we have this guy to thank for helping us get through that misunderstanding. This is John Muir, of course, the famous conservationist who spent many, many years, many summers especially, exploring the Yosemite and the Sierra Nevada. And it turns out that John Muir was the first person to really definitively discover a glacier in the Sierra Nevada. And that was in Yosemite in the Clark Range, not too far from Yosemite Valley. And he's got this really cool description here. I don't need to read the whole thing to you, but basically he set out to try to determine whether he could find, as he said, a living glacier, something that was not relict, but an active glacier. And he climbed up over a moraine, observed this big field of ice that had many of the defining characteristics of a glacier, and ran around very excitedly saying that he had found one of these living glaciers. So that was in 1871, I think, when he found that glacier. He was met with some skepticism, and so he later, the following year, had to set out to try to rectify that. I'll talk more about that in a second. But since Muir's first discovery of glaciers in the Sierra Nevada, we now have a much better understanding of the extent of modern glaciers. And a survey that was done in 1980, so a while ago now, shows all the modern ice features at the time in the Sierra Nevada in red there. So these are glaciers. They are also ice patches. So a key thing about glaciers is that they move, right? They slide and the ice deforms under its own weight. So there's movement of that ice. That's why it's a living glacier. When you have ice that is not moving, it's stagnated, or maybe it's not thick enough to ever move. We call that an ice patch. It persists from year to year, but it's not moving. And finally, we have perennial snowfields. These are snow, not ice, but they also persist from year to year. So there's, in 1980 anyway, there were more than 1,700 of these ice features, including 122 true glaciers at the time. And these glaciers, which are moving, were mostly found in north or northeast facing cirques at the highest elevations of the Sierra. So take the highest peaks, go to the north or northeast side, there's a good chance you're going to see at least a small glacier. And this photograph is showing the largest glacier in the Sierra Nevada. This is the Palisade Glacier, which is found in the mountains west of Bishop. The glaciers that I'm most familiar with are those in Yosemite National Park. These are the Lyell Glacier and the McClure Glacier. And Mount Lyell is the highest peak in Yosemite National Park at 13,114 feet, I think it is. Originally, like back in the late 1800s, the Lyell Glacier was one continuous large glacier. I'll show you some pictures of that in a bit. At the time that this photograph was taken in 1972, it had retreated back so that there were basically two lobes of it, separated by a bedrock ridge, the east lobe and the west lobe, right? So we're just going to call that the Lyell Glacier, even though it's shrinking into a bunch of these smaller lobes. And then just to the west of that, underneath Mount McClure, which is top 5 of Yosemite's highest peaks, is the McClure Glacier. And it's really like the next door neighbor of the Lyell. And it too is one of Yosemite's remaining glaciers. These glaciers are at the headwaters of the Tuolumne River. They are the source for the Tuolumne River, which flows in your direction, and is an important water source for a lot of Central California. So these glaciers are significant in that sense also. Okay, so this photograph again was taken in 1972 from an airplane. And a few years ago, a friend of mine was able to basically reproduce that photo by directing an airplane to get to that pretty much same exact spot and retake the photo. And you can see there's been a lot of change to those glaciers since 1972. They are much smaller. We call that retreat. They've retreated back toward the cirques that they're in. They have thinned considerably, and they've gotten much dirtier. Like there's a lot more rock that's exposed on the surface of the glacier. And that's because glaciers have rocks embedded all within them. But as the glacier is shrinking, getting thinner, the rocks that are scattered throughout them become concentrated on the surface. And that also tends to darken the surface, which increases the melt rate because the darker surface absorbs more energy. So you get these sort of feedbacks as the glaciers are retreating back, that they start shrinking faster and faster. So that's kind of the state of the glaciers, or the first snapshot that I'll give you of the sense of the glaciers. But a point that I want to make that I think is really important with Lyell and McClure glaciers is that they have been studied for a long time. And I think that's primarily a function of them existing in Yosemite National Park, which has been a famous place for a long time. But the records of scientific research go back 150 years. These are some of the longest records that we have anywhere in North America. And again, it really did start with John Muir, first with his discovery of glaciers in 1871. And then I think reacting to some skepticism among more formally trained geologists, he went out the following year with Galen Clark, who was an early guardian of Yosemite. And he went to the McClure Glacier specifically to measure its movement, right? So earlier he observed what he thought was a living glacier, but in 1872, he set out to actually see if they were moving. And he did this by planting stakes in the ice, and then of those stakes over roughly a 46-day period. So he determined that the McClure Glacier during that time period was moving about an inch per day. So measurable movement, truly a living glacier. The history of research continued into the 1880s with scientists from the US Geological Survey, Israel Russell and G.K. Gilbert. These guys were primarily exploring the Mono Basin, but went up to the high peaks and made a trip, a couple of actually, to Lyell and McClure glaciers, and importantly, took a lot of photographs and made a lot of good maps. So this is one of the maps that they made showing the Lyell and McClure glaciers. North is pointing down in this case. But you can see the Lyell Glacier was not two lobes at that time. It was connected in a couple of different places. It was one big span of ice. And an important note on this map is where it says moraines now forming. So a moraine is a ridge of rocky debris that's left along the margins of a glacier. It's transported from higher up down to the edge. And then when the ice melts away, it leaves that rocky debris there to form a moraine. And the fact that in 1883, the Lyell Glacier was right up against the terminal moraines means that it's basically the largest that it's been, at least since the end of the Tioga glaciation 20,000 years ago. And I should point out that the glaciers are not the last remnants of the Tioga glaciation. They formed later during the Little Ice Age. So based on some dating we've done, they may be a couple of thousand years old at the oldest. Maybe they're 1,000 years or a little bit younger than that on the whole. So they're fairly young, but in 1883, they were still up against their maximum positions, which means all of the data that we have since 1883 captures the full history of retreat of these glaciers since they formed during the Little Ice Age. And here's a photograph also taken by Russell's team in 1883. It's black and white, of course, but there's a ton of detail in there. And this is something I do every year, is go to the same photo point and retake this photo, because there's a lot of information that you can get from simply repeating photographs year after year. And after the USGS involvement, they were involved until the early 1900s. But after creation of the National Park Service in 1916, roughly 15 years later, at the urging of USGS scientists, Park Service started making measurements of the Lyell and McClure Glacier. Annual surveys where they would go up and measure where the edges of the glacier were. They would measure across the glacier to see if the surface of the ice was changing. And bear in mind, they were not doing this because of being worried of anthropogenic climate change, right? I don't know that there were very many people thinking about this in the 1930s, but they knew even back then that glaciers are sensitive indicators of climate change, and that they ought to be monitoring these glaciers to get a sense of climatic changes. And that could include glacier growth. They just thought that monitoring was important. And we owe them a debt of gratitude for that, because this has been really important that we're still working with. Each year after their surveys, they would write a report on their activities and report their data. And they included a lot of really great photographs. And I'm just showing you a couple here, not only to give you a sense of adventure, which is definitely a big part of going up to these glaciers and exploring them, right? You get to walk around on the ice, you get to cross these big chasms in the ice called crevasses. You get to explore ice caves, crawl back into these caves that formed within the glaciers. But I also show you these because I am highly impressed by these Park Service rangers wearing their full uniforms on the glaciers and in the ice caves. They have flat hats, they have ties, they are very professionally dressed, 15 miles from the road and way up there at almost 13,000 feet. So they set a really high bar for future park rangers. Let me just say that this period of annual surveys by the National Park Service was really intense in the 1930s and 40s. There was a bit of a break during World War II, not surprisingly, but right after they went every year through the 1950s and into the 1960s, and it started faltering. They missed a few years, and then they missed quite a few years, and the last survey was in 1975. So interestingly, we have more information about the glaciers from the 1930s than we do from the 1980s. And I don't have a great explanation for why those surveys faltered, but it probably was that there wasn't a motivated person carrying the torch for this project at the time. Fortunately, around the 1980s is when we start to have satellite imagery and other maps and things that we can use to fill in the gaps. But it wasn't until I was hired as Yosemite's first park geologist in 2006 that we picked up the surveys again. And I've been going at least once every year, sometimes many times each year. I think I've been up to the glaciers almost 30 times now. So yeah, it's one of my favorite places to be in the park. So I plan to keep going. But we've been not only conducting the traditional surveys of the glaciers, but also employing a lot of new techniques that I'll be talking to you about. I'd say on one occasion, I brought a flat hat and a tie, and I dressed up like the old park rangers, and I explored an ice cave just to get a sense of what that was like. And it was really fun to do that and have the link with past history, but it's not the best field uniform, I have to say. I prefer Gore-Tex. But in any case, that was kind of a cool thing to do. Okay, so among we've done over the years to measure the glaciers, monitor their changes, and also keep our connection with history. It was 10 years ago now that I realized in 2012 it was going to be 140 years since John Muir made his stake measurements, right? He did that in August through October of 1872. So, and just recall, that's a 46-day period. He measured 47 inches of movement. So he determined that the McClure Glacier was moving at about an inch per day. So 140 years later, we decided to set out and redo Muir's experiment. Not necessarily use the same techniques, but basically making the same set of measurements. So it's kind of like, I was interested in digging in a little more to exactly how Muir did this. And I didn't find a lot of information, actually. His field notes are kind of hard to read. And what he had published was pretty simple. The positions of these stakes were determined by sighting across from bank to bank using a plumb line made of a stone and a black horsehair. That was his methodology. I still don't know all the details, but I'm pretty sure, first of all, a plumb line, stone on a black horsehair. I don't know if you can see this. This is a stone from the McClure Glacier hanging from a horsehair, which I collected from a horse in Tuolumne Meadows, and it is black. So this is like part of his key technology right here. And I think what he was doing was using the plumb bob to describe a vertical line. He was set up off or somewhere, and he had this set up, and along that line going across the glacier, Galen Clark went out there with these 7-foot tall spears of white bark pine that they were using as stakes, and he would plant them in a line across the glacier, along that line, even with the plumb bob, right, and sighted to a distant peak. So they put those stakes in the glacier, then they came back 46 days later. Muir set up on the same spot, had the same measurement of the plumb line. Galen Clark went out there and found how much the stakes had drifted from their original position, and then they measured them somehow. I don't know what the precision is on his number, but again, using those techniques, they came up with 47 inches over that 46-day period, or about an inch per day. So on the exact same days in August and October back in 2012, we put stakes in the glacier. They were not white bark pine stakes. They were made out of PVC and metal. But in essence, the technology was the same, right? We're putting things in the glacier that will drift as the glacier moves, and we're measuring them from fixed positions off the glacier. And instead of using the horsehair plumb bob, we were using laser rangefinders and very high resolution GPS, global positioning systems. But again, the essence of the measurement was the same. So we put these stakes in various places in the McClure Glacier. We tried to sort of have the arrangement of the stakes be the same as Muir's time, but we recognized that the McClure Glacier was a lot bigger when Muir made his measurement, right? It was like, it's roughly 20% of what it was back in 1872. So it's a much smaller glacier. For that reason, I wasn't sure if we'd be seeing any movement at all. But the really amazing thing is, after measuring the movement for 46 days in 2012, our end result was that the glacier was moving about 2.5 centimeters a day, which is about an inch a day. So we basically got the same measurement that Muir had 140 years earlier on a glacier that's much smaller. So according to Muir's definition, the McClure is still a living glacier. It's still moving at the same rate that Muir measured it 140 years prior. And I was really surprised by that. I don't necessarily think it's a great sign of health. It's probably moving faster because the surface of the glacier is steeper, and that drives accelerated movement. And also there's more melt, which means there's more water getting down to the bottom of the glacier, reducing the friction down there and allowing it to slide faster. But it is still moving, which is an important finding. And when you visit the McClure Glacier, you can actually see evidence of this movement in various ways. There are crevasses. There are these, again, big cracks in the glacier that typically form as the glacier's moving over a bump in the bedrock below. There are also ice caves in the glacier, and the surfaces, like the ceilings of these ice caves, have these long striations in them that are formed in the ice as the ice is planing over small bedrock protrusions. And so when you're on the glacier or in the glacier, you can see a lot of evidence of movement. And I've even been on it once and heard and sort of felt it lurch a little bit. So it is still a moving glacier, and we've measured that, but there's good signs for it in the field. One final cool thing about our study of the McClure Glacier back in 2012, which is that when we were reading through some of the Park Service reports from the 1930s, we found a description of them finding a piece of white bark pine at the toe of the glacier and taking it back to the park museum. And that's the last that I had ever heard of it. So I contacted our park archives and said, hey, do you have a 7-foot tall spear of white bark pine, be one of John Muir's stakes, and they said, give us a little while to look around. A couple days later, they came back and said, yeah, we've got it. They didn't even really know they had it either, turns out. But here it is. It was broken in half at some point, maybe just to get it out of the field. But this is one of the original white bark pine stakes that John Muir and Galen Clark created up there and used to measure the movement of the McClure Glacier. And when you hold it in your hand, as I was lucky enough to do, you can still see the axe marks on it from John Muir's axe. So it was a really cool piece of history. And that, coupled with actually getting the same result that Muir did, just made me feel really connected to that history. Sad to say, the story is not the same nearby at the Lyell Glacier. We did the same thing there. We put a bunch of stakes out on the ice. We measured the stakes over that same time period that Muir did. And for good measure, we actually measured those stakes over multiple years. And the result there was a bunch of zeros. Basically, we found that the Lyell Glacier is not moving anymore. It has stagnated, probably because it's too thin to flow under its own weight. And because it's not moving anymore, I think you could make a good case that we shouldn't call it the Lyell Glacier anymore. It would be called the Lyell Stagnant Ice Patch, which definitely doesn't have the same ring to it. But strictly speaking, it no longer meets the criteria for a glacier. It's not moving. And this is the second largest glacier in the Sierra by surface area. So that's kind of shocking that it's not moving anymore. Okay, so pulling together all the various information that we have, beginning with Muir's measurements of movement, as well as the really great maps and photographs from 1883 up to the present, we can make maps like this, which is change in surface area of the glaciers through time. The dark blue colors are the earlier extents, the lighter colors are getting closer to the present. And you can see that all of the glaciers are shrinking back. The east lobe of the Lyell Glacier especially has lost almost everything that's there. There are just a few tiny patches left. We can do trend analysis here to make some predictions about when these glaciers will disappear just by surface area. But it turns out that that's just a two-dimensional snapshot. It's helpful, but a more important thing to be measuring for these glaciers is not the surface area, but the volume, right? The three-dimensional volume of ice. And how do you do that? You know, especially when a lot of your data sources are from the late 1800s, early 1900s. So a couple of years ago, we set out to try to reconstruct the historical ice surfaces in the digital realm, using field mapping, historical photos, historical surveys, GPS data, LiDAR data, which is laser scanning data, in this case, mostly from airplanes that are making really precise maps of the glacier surfaces each year, and also satellite imagery, mostly from the 1990s to the present. And basically what we can do, we also incorporated a lot of these field surveys. Again, I showed you some pictures of this earlier on, but this is just an example of some of those cross sections across the glaciers that the Park Service made beginning in the 1930s, showing the glacier ice surface coming down through time. So we have enough information that using computers in the digital space, we can start to reconstruct these surveys. So this is the Lyell Glacier here, and the red line is the outline of the perimeter of the glacier as it looked in 1883. And there's actually a lot of good information in that line because it's a three-dimensional line, right? So for starters, we just interpolate points across that surface. We can create a mesh surface. So we're connecting points at those different elevations. It's kind of like, stretching a piece of saran wrap or something and conforming it to all the elevations along the margins of the glacier to come up with a surface. And then we can take that mesh, connect all those points and make it a surface that looks like the glacier did in 1883. So we often use what are called digital elevation maps or digital terrain maps. And those are quite common to have for the modern times. This is a digital elevation map from 1883 based on that reconstructed ice surface. So this is another way to look at it, right? Sort of an oblique view. The top view is a photograph of the Lyell Glacier as it looked to a real person in 1903. And the bottom is our modeled ice surface, trying to reconstruct that ice surface in 1903. And in my view, it's a pretty good fit, right? Once we initially constructed that surface, we then tweaked it a little so that it fit the photographs as best as possible. And this is our digitally reconstructed model ice surface for the Lyell Glacier. And what I want to show you now is another view. This is the east lobe, and I'll just march you through. Again, these are reconstructed surfaces, but they are representing the retreat in 3 dimensions of the Lyell Glacier since 1883. So that's 1883, 1903, 1931, 1944, 55, 72, 1993, 2003, 2012, 14, 15, 18. Right. So you can see the full retreat of these glaciers. Another thing we can do with these reconstructed surfaces is figure out how much the glaciers have thinned in that amount of time. So how much the surface of the glacier has come down. And the more red colors there represent greater degrees of ice loss. And there has been up to 75 meters, which is more than 200 vertical feet of thinning of these glaciers since 1883, between 1883 and the present. So big changes, right? It's not just the footprint size that's shrinking, but the thickness of the glacier is really shrinking as well. And again, that's probably why the Lyell Glacier isn't moving anymore. Okay, then there's one more thing that we would like to do, and that's not just measure how much change has occurred from one time to another, but try to get a sense for how much ice was there in 1883 and how much ice remains. And that's previously been really tricky to figure out because you can't see through the ice. You don't know how deep the bedrock is. We don't really know what's underneath the glacier. And we still don't know that for sure, but as the glaciers get smaller and smaller, we can place better limits on that. And so what we did in this approach was to develop a bunch of cross sections, utilizing the bedrock adjacent to the glacier and then projecting that underneath the ice so that it then meets the bedrock on the other side of the cross section. And when we do that and then connect all those cross sections together again into a reconstructed surface, we can have a pretty good sense of what the bedrock looks like underneath the ice. And a couple of years ago, we went out and did a little bit of field calibration of this to make sure we're not completely wrong here. And we did that using this sort of funky contraption shown in the photograph on the right, which is called a steam drill. And it's sort of like a big pressure cooker that you take into the backcountry. You fill a canister with water, you have a little propane stove that heats the water in that canister, pressurizes it, and then you send it through a hose with a metal tip to it, and you generate a really high pressure stream of steam, and then you use that steam to melt a hole in the glacier. And so when we do that, we can basically melt a hole down to the bedrock with as much hose as we had. And we were limited at about 13 meters of hose. So that's as far as we could go. But we probed around the edges and we found in general that our calibrations matched pretty well within typically a meter or two of our estimated bedrock depth. So that was really cool. Another thing that was really cool, that person on the right is a high school student at Lee Vining High School. Her name's Ellery McQuilkin. And I've been mentoring her on this glacier project. In fact, the steam drill was actually her idea, and she borrowed it from another university researcher. And I just want to give a shout out to Ellery. She's a really impressive young scientist, and I think she's going to be a glaciologist someday, if I had to bet. Just to show you, this is another example from the McClure Glacier. Here, we're thinking that the maximum glacier thickness is about 40 meters, which is a little more than half the Lyell Glacier, but still not tons of ice left, particularly when in dry, warm years, we might lose 3 or 4 meters of ice thickness in a single year, right? So given those trends and given the remaining thicknesses, it's reasonable to think that these glaciers might last 10 to 20 years, something like that. Warm, dry years like this one is turning out to be are not good years for these glaciers, right? They suffer a lot during the droughts. So in the end, using these digital reconstructions of the ice surface, we can come up with the total volume of ice that was present in these glaciers in 1883. That was something like 47 million cubic meters. Cubic meters about the size of a washing machine. So, 47 million of those. That's how much ice was there in 1883. When we do that same calculation for 2020, it's about 5 million cubic meters. So obviously huge reductions of ice. And that turns out to represent a 90% loss in volume. So these two plots are showing on the left the area loss of the glaciers from 1883 to 2020. And on the right, the volume loss for the glaciers over that same time period. So the line represents the actual data. The shaded areas around them represent our uncertainty in those measurements. And there's larger uncertainty in the volumes because we use those digital reconstruction methods, which are not direct measurements, right? They're estimates with some error. But the trends are pretty clear. The glaciers have always been losing ice since 1883. We haven't seen any sustained period of time where they were actually gaining ice. They've been in net decline since 1883 and the end of the Little Ice Age. There are times when that line is a little bit steeper, sometimes when it's less steep, but I do especially want to point your attention to this period right in here, which is 2012 to 2015. That was our last multi-year drought. And again, droughts are really hard on these glaciers, not only because there isn't snow in the wintertime to build more ice, but the temperatures are really warm. So you melt through that snow and then melt into old ice for weeks or months during the summer. So the glaciers lose a lot. And I'll just say last year was a pretty warm, dry year. The glaciers retreated a lot last year, and I'm fully expecting this year to be similar in that regard. So I can't make a precise prediction of when the glaciers will disappear entirely, but it's probably within a decade or two. Certainly for Lyell Glacier, it's probably the one we're going to lose soonest. Okay, now to take you back to this plot that I showed at the beginning, right? This is showing the pace of natural climate change on planet Earth going back 800,000 years. And I sometimes will get the question, okay, so Yosemite's glaciers are disappearing. What's the big deal? Like, why is this significant? We know that Yosemite has had large glaciers in the past. They've disappeared before. Yosemite Valley used to be full of ice. There's no more ice in Yosemite Valley. All true, all correct. And that was happening for natural reasons as shown in this plot due to these orbital parameters. The other thing you'll see in this plot, and I kind of hid this from you last time, is what's happened with CO2 in the last 150 years or so, but really in the last couple of decades, beginning with the Industrial Revolution and increasing into our very active emission of carbon dioxide and other greenhouse gases. You can see that the present value of CO2 in the atmosphere is just way higher than anything in the past 800,000 years. And that, simply put, is primarily coming from fossil fuel combustion. That's putting the CO2 in the atmosphere, which is causing the greenhouse effect and causing temperatures to warm. We haven't yet seen Earth's temperatures spike the way the CO2 is spiking, but it's really just a function of lag time. It takes a while to heat up a planet that has a lot of water and ice on it, but that is happening, as you know. It seems like every year or two, we're talking about record warm temperatures. So the retreat of the Lyell and McClure glaciers, sure, it's happened before, but the reasons that the glaciers are retreating now are fundamentally different than the reasons why glaciers have retreated from Yosemite in the past. This time it's being driven by anthropogenic increases in carbon dioxide. So what will happen when these glaciers disappear, right? I've increasingly spent a lot of time thinking about this, and we're starting to do more studies beyond just the glaciers themselves and looking a little bit downstream. The first thing we know is that the melting ice sustains the upper Tuolumne River base flows. So in the summer and late fall, after all the snow is gone from the landscape, the uppermost Tuolumne River might go dry, except that there's a lot of water being supplied to it by the melting glaciers. And the warmer it is, the more the glaciers melt, the more they supply the river. So they are really important in kind of buffering the base flows. And when the glaciers disappear, that buffering effect will probably also be gone. We expect that the temperature of the water will warm up as the glacial melt diminishes. And that's going to affect downstream aquatic and riparian ecosystems in ways that we don't have a good handle on yet. This is a little bit of a complicated plot, but let me just say that these are records from 2 stream gauges, one of which is close to the glaciers. That's the light blue one. And that's the dark blue one. And the light blue one is from Tuolumne Meadows. So it's down there by the Tuolumne campground, 15 miles below the glaciers. What you see, especially during the drought years in the late summer and fall, is that those 2 stream flow amounts basically converge, meaning that there's not a big difference in the amount of water just below the glaciers as there is in Tuolumne Meadows. The upshot of that is that late summer season, the meltwater is providing something like 75% of the water flowing in the uppermost Tuolumne River. Now, this is not a huge volume of water. It's not a threat to San Francisco's water supply, for example. But for the alpine region there and the subalpine region adjacent to the glaciers, that meltwater is really important. And when the glaciers disappear, there's a much greater chance that these base flows are going to be much lower, possibly even drought. So again, the overall volume of water is small, but the buffering effect is large. And 2021, 2022, these are drought years again. We're seeing these same sort of patterns. I want to basically end here with a couple of photographs that I took. Well, the original photo is from 1883. The bottom photograph was taken last September. And in some ways, these photographs really tell the whole story, right? You can just see big changes in these glaciers. These are probably the biggest changes that are visible in Yosemite and happening faster than just about anything else. And here's another view of the glaciers, 1883, and then again in 2021. So I think it's pretty easy to visualize how these glaciers are just going to disappear. And then there's just one more thing I want to touch on, and that's the human element to all of this, which is not something that I typically have spoken about a lot as a scientist, but I think it's important. This is a photograph of me up at the glaciers with my daughter when, I forget how old she was, maybe 13, 12, something like that. I just felt like it was really important to get her up there and seeing the glaciers before they disappeared. And this is a little watercolor sketch that she made of the McClure Glacier when she was up there. There's really no way that we're going to keep these glaciers from disappearing. The timescales are too short. But I do think that they're important symbols of climate change affecting a place that I certainly love in Yosemite. And I also think that it's important to share this story, which is why I go back to the glaciers year after year, why I bring a lot of different people up there with me and show as many people as I can these glaciers, and why I'm talking to you tonight. So these are a couple of summary points. I think you can just read those, and I will stop here. Thank you for your time, and take any questions that you might have.
Hi, Dr. Stock. It's Susan Kerr, Anthropology. I'm here to ask a few questions that popped up on the chat. There's a lot of excitement out there, I just have to say, a lot of students coming in from different classes, but some specific questions. Linda asked, how long does it take to get to the glacier? And somewhat related to that, is it possible for the public to go access the glaciers and hike on them?
Mm-hmm. So the glaciers are about a 15-mile hike from Tuolumne Meadows. That's where you start the hike. And you hike up the Lyle Fork of the Tuolumne River. The first 10 miles or so are pretty easy and flat. And then the last 5 miles are quite steep. So I've been up and back in a day, but I don't recommend that. It's much better to do as a trip. When I do the glacier survey trips, which are always in late September, those are typically 4 or 5 day trips. And yes, you can go visit the glaciers yourself. You'll need to get a wilderness permit through the park. And those can be a little difficult to get. But if you can get a wilderness permit, you can hike up and explore the glaciers yourself. And I would be careful when you do that. Don't travel on the ice unless you have experience using ice axes and crampons and navigating steep icy terrain. But you can certainly go to the base of the glacier and maybe walk around the edge. And again, I highly recommend you do that because there's not a lot of time left to see them.
All right, good advice. Giselle asked, what happens when there's no more glacier? I think you kind of addressed that a little bit, but is there anything else you might want to add?
We're still exploring what the ecological effects of that are going to be. I mean, I can make some guesses. I think things that live in the stream and things that eat the things that live in the stream are probably going to have a harder time because the stream is going to be warmer and smaller and maybe even go dry at times. From a human standpoint, I think backpacking up there will be kind of different, especially if the stream is dry, right? You'll have to carry more water. And then there's an element to this that I'm still wrapping my own mind around, but it's a really amazing experience to go up to these glaciers, right? To me, it's utterly unlike anything else you can do in Yosemite. It feels like a totally unique place. And when the ice disappears, I think like that sense of adventure will also kind of disappear. And then finally, and this is my last bullet point here, I talked about a history of research that goes back to John Muir in 1872, right? That's 150 years. And when the glaciers disappear, that whole history, that arc of history ends, right? There's no more study of the glaciers. And it's possible that I'll be the last person to actively study them. And that feels kind of weird too, because that's not usually the way it is in geology. Usually you just keep building on the work of other people. But yeah, when the glaciers go, the research ends also. That's sad.
Yeah, that is. So that kind of brings up my question, which is, you were hired in 2006 as a first park geologist at Yosemite National Park, which is based on fancy geology. How did that happen? How did it take so long?
I don't know. I don't know. I will say that the Park Service in general it's kind of new that the Park Service, it's sort of new that the Park Service is a science agency. I think the Park Service went a pretty long time with naturalists, and they are scientists, but to have dedicated research scientists is a kind of a new thing. I think it might also be that for a long time there was a sense that the geology in Yosemite was just static, Half Dome just sits there. Why do you need a staff geologist? But turns out that that's not the case, right? The glaciers aren't the only thing that are behaving dynamically and changing rapidly. The other thing that I do here in Yosemite, I spend a lot of time in this, is studying things like rock falls and rock slides, which close roads and trails and injure and kill people sometimes, right? And that's very much not static geology. So I think it was probably the accumulation of a need to have more geologic expertise and also just build up the scientific capability of the park. So whatever it was, I'm glad they hired me.
Yes, thank you. Katie asked, can stagnant ice patches or any other sort of used to be glacier turn into a glacier again?
Yes. What it would take is a turnaround in our present climate trends so that things start to get colder and we have a bunch of really big winters in a row. And by a bunch, I mean probably multiple decades of above average snow. And that, coupled with cold temperatures, would form more ice and the glaciers would grow again. So theoretically, it is possible. I'm pretty sure someday these glaciers will grow again. but I have no idea how long that will be from now. Probably a pretty long time.
Okay, thanks. Bill asked, what does normal movement look like in a glacier compared to the recent sort of post-anthropogenic movement? I think just the glacier like you were measuring, perhaps.
Okay. Interesting question. I'm not totally sure what normal is. Each glacier is different. The bigger the glacier, the faster it will move. Again, we're talking about inches per day, but there are glaciers on the planet that move like many, many feet per day, right? These are really big glaciers. So I think what's the really interesting thing in our study of the McClure Glacier was that even though that glacier between Muir's time and when we measured it lost like 80% of its surface area, it was still moving at the same speed. And it's for a different set of reasons that it's doing that, but it's still moving. I was expecting it to slow down, but at least at that time it hadn't slowed down. I should say that this summer represents 150 years since Muir made his measurement, and we're going to go out this summer and repeat that measurement again. So we're going to bring stakes and all of our tools and measure the glaciers on those same days that Muir did and see if we're still getting an inch per day kind of measurements. I would actually be shocked if we did, but it's possible. I'm expecting the glacier to have slowed down in that amount of time because it's even smaller now than it was in 2012.
All right, sounds good. So I think you and George need to have a conversation after because he has a lot of questions.
Okay.
But
George,
let me start with,
me.
in terms of measuring the volume, or at least the glacier, he said, wouldn't explosives and seismic measures work for that?
Well, we probably wouldn't use explosives in the park, but good point. There are ways of imaging the glaciers. The most commonly used tool is ice penetrating radar. So you're basically sending radar waves through the ice, it bounces off the bedrock and comes back. And the problem with that technique and just about all these other imaging techniques that you mentioned is that the Lyell and McClure glaciers are just too small for those to work effectively. We haven't tried them on these glaciers, but I've been told by colleagues who have tried them on small glaciers that it's really noisy. You basically get so much noise in the data, it's really difficult to pin down where the bedrock is. So yeah, I would like to be able to use those techniques, but I don't think they're going to work so well for us here.
Okay, sounds good. He also asked, how can you distinguish between the close of the Little Ice Age and the conditions secondary to climate change affecting the current retreat?
Good question. And I would say from the Lyell and McClure glaciers alone, we're not really able to tease that out. I think the essence of the question is, how do you know whether or not what's happening with the glaciers now actually has any human influence or not, right? It's an interesting question because you could actually start by saying, was the end of the Little Ice Age in some way related to human activity? I mean, it coincides more or less with the beginning of the Industrial Revolution and our industrial scale of using fossil fuels. But I think early on, the human effects were probably fairly small and then increasing in magnitude. And I would just say that there have been studies integrating lots of data from lots of glaciers around the world. And they show that beginning in the 1970s, the dominant effect was anthropogenic. And prior to that, mostly it was just sort of end of Little Ice Age. So hopefully that answers the question. It's a combination of both with an increasing human influence.
Okay, sounds good. And the last question that I saw, and I think Bill might have some questions after mine, are after the end of the Tioga, were there glaciers in the Sierra? Let me see. Or were they completely gone?
We're not totally sure, but the best evidence is that they were completely gone. And this evidence comes mostly from cores of lakes that are kind of adjacent to, well, they're up in the high country. And what you see is that the lakes are exposed when the Tioga Glacier retreated back. And then you see sort of a shutoff of the fine-grained sediment entering the lake that's usually a function of glaciers being on the landscape. They grind up the rocks and produce this very fine sediment. So that sort of shuts off for most of the last 10,000 years after the end of the Tioga glaciation. And then a couple thousand years ago, we start to see it pick up again, and that's one of the reasons why we think that the Lyell and McClure glaciers might be 2,000 or 3,000 years old, because they started forming again at that time and then really grew during the Little Ice Age. But to answer the question, our best guess is that for a period of time after the Tioga glaciation, there was really no ice in the Sierra Nevada.
Okay, cool. Bill, did you have a couple of questions you wanted to ask?
Yes, I do. I think I'm just going to start with a couple other questions I see in the chat, and then I have a couple of questions. Jeff asks, since most of the volume of both glaciers are already gone, shouldn't we have already seen the impacts or signature on ecosystems with ongoing base flow reductions?
Probably. I mean, I'm not sure if we would have seen the majority of the changes. I actually think the biggest impacts will be in the future when we start seeing like a total lack of glacier meltwater contributions. But I think that's a good point. There probably has been a lot of change already. And the truth is we haven't been looking carefully enough to detect that. You know, we haven't had any studies specifically dedicated to that yet. This summer will be the first summer that we're actively investigating the biological dependence in the lakes, in this case specifically on glacier meltwater.
And I think that's related to the buffering effect. And I'm wondering if you could just briefly explain that again, the buffering effect. You know, because they're small relative to the total snowpack, and yet it really does make an impact, a significant impact on, so if you could explain that again.
Yeah, maybe a good way to start explaining that is to share a story. There are a couple of places in the Sierra Nevada where you have two watersheds side by side. And I've been to these watersheds in the late summer or fall. One of the watersheds has a glacier in it, the other one doesn't. And when you go to the one that doesn't, it's basically dry. There might be just a little trickle. And then when you go to the other watershed that does have a glacier in it, it's got a very robust, cold stream flowing down it, right? And these are similar sized watersheds. The difference is that one has a melting glacier that's supplying water to it. So that's the buffering effect that I mean. The watersheds without glaciers, you know, they might have a very healthy runoff when the snow's melting, but once the snow's gone, that's it. They're done. They mostly go dry. Whereas the watersheds that have glaciers, they don't hit rock bottom like that. You know, the snow will melt, they'll get to a low flow, but then that low flow will just keep sustained throughout the summer and fall. And it's cold water because it's coming from melting ice. So yeah, that's the buffering effect. And sorry, what did I catch the question?
Yeah, I think so. I mean, and so what also is happening is there's all kinds of impacts on vegetation, like in really complicated ways, right?
Yeah.
Like certain vegetation that requires that small trickle amount of water that's constant, even though it's not a lot and it's cold. So is related to that, is the Park Service studying that? Like, I mean, I'm sure like how the vegetation is going to change, how all that, the ecosystems will change in the Sierras once the post 2040.
Yeah. Well, first of all, like on a large scale, we are in collaboration with a lot of other research scientists. So there are a lot of studies going on about large scale vegetation changes in the park. And as I said, this is the first summer where we're starting to actively investigate the influence that the glacier meltwater has on the aquatic and riparian ecosystems, right? So, you know, to me, it's pretty clear that there are a lot of plants that grow along the riverbanks in the uppermost Tuolumne River that are adapted to having a constant supply of water. And when that isn't present, those plants probably won't be able to exist anymore. That's quite possibly true for the macroinvertebrates that live in the streams and the lakes. And then again, you know, those are sort of the bases of the food chain upon which a lot of other things rely. So we don't know the full cascading effects yet, but there are going to be effects, and this is the first year that we're starting to look into that.
Right, a lot of knock-on effects. Before I ask any more questions, I just want to encourage students and anyone to put more questions in the chat that you have. And I'm going to ask a question, Richard's question, in a minute. But before I get to Richard's question, I do want to ask you about this issue of, like, I imagine it was like a law of glacier movement and growth, and is what's happening in the Sierras basically the same dynamic as what's happening at Glacier National Park in Montana, Iceland, Antarctica? Is it basically the same kind of physics and changes in glacier and the effects of global warming? Is it the same everywhere, or are there like unique things about the Sierras that are unique to the Sierras in terms of these changes?
I actually don't think of the Sierra glaciers as being especially unique. I think it's what we're seeing in the Sierra is really similar to what we're seeing elsewhere in the lower 48 states. So Glacier National Park is a great example. Those glaciers were a little bit larger, say in the 1800s, but they've also lost something like 80% of their surface area, probably something like 90% of their volume over that same time period.
Like Grinnell, right? Grinnell, yeah.
Yep, that's a good example.
Okay,
then,
Rich, yeah, I'm sorry.
Oh, sorry. Just, for larger glaciers, I think you just scale that up. Some of the larger glaciers at higher latitudes maybe haven't lost 90% of their volume yet, but the magnitude of change for those glaciers is much, much larger, right? You talk about it in terms of cubic kilometers instead of cubic meters. Occasionally there'll be an odd glacier that's advancing for one reason or another. Sometimes it's because the warmer climate is wetter and still cold enough to fall as snow. Sometimes the glaciers just surge for a couple of years and then stop, but those are really outlier. The vast majority of glaciers are doing what Yosemite's glaciers are doing, which is they're shrinking back.
Thank you. Richard Anderson has a question. Are state and MID water managers sophisticated enough to factor in? Okay, so there's a question about, I'll just make the large question about the snowpack. I know we've been talking about glaciers. Is a different person focused on snowpack? I imagine there's a whole other group of folks focusing on the snowpack. But what is if you can comment on the projected, our frozen reservoir in the Sierras, what are we looking at in 2040, 2050 in terms of capturing all that runoff so that we have a reliable water supply, given that it won't be spread out right through the spring and summer if the snowpack disappears? Could you comment on the latest knowledge you have about the disappearing snowpack and how that'll affect our water supply? And I know it's a complicated question, so.
Yeah, and I'm only qualified to sort of speak about the Yosemite specific science on this, but it certainly is the case that climate change will most likely lead to a reduction in snowpack in the mountains. And as you point out, there's an awful lot of water that's stored in the mountains, right? We don't just store water in human-made reservoirs. The snowpack is this huge natural reservoir that's kind of on the same order of magnitude as all of our constructed reservoirs. So what warming temperatures will do will basically raise what's called the snow line. So that's when a typical winter storm hits the Sierra Mountains, snow might fall up above about 6,000 feet, maybe something like that. It'll vary from storm to storm, but on the whole, that's a typical winter storm. As the planet warms and these storms come in warmer, maybe now they're falling as snow above 9,000 feet instead of 6,000 feet. And in the Tuolumne watershed, that's a huge increase in watershed area, no longer falling as snow. It's falling as rain, and that runs off immediately. So you've lost that storage of water in snow, for many, many months. It's just going to run off immediately. So that's one issue, regardless of whether the amount of precipitation actually increases or not in the future. And that's not well known. It's probably going to be more variable, but we don't know what the average, if that term even applies, what that will be. But we know that the storms will come in warmer, and so there'll be less snow. The other thing I'll say is that we've had quite a few very warm and dry years in the past decade, and we're looking at another warm and dry summer here. And so that also is the snowpack's taking a big hit in those years, right? This is going to be a really low snowpack year. And I'll just say, in addition to monitoring the glaciers, again, starting this year, we're going to be monitoring the permanent snowfields in the park, which we have not done in the past. And I expect to see some big changes in those in the coming years too.
Okay, and we have got two more questions, I think. Okay. The question that the other question I have has to do about climate change education, and how, I think you mentioned this, that the story of glaciers, and especially the story of disappearing glaciers, becomes a easy communication symbol for the effects of climate change, in a way that the public can kind of easily understand the effects of climate change. So I'm wondering about where that discussion is now. For example, those who are maybe skeptical about climate change, they're not sure what an impact we have. Are they, focusing on those few outlier glaciers and saying, look, some are still growing? Or is this now pretty much been, even in the public discourse, kind of resolved? Can you speak a little bit about that? And then I have one more question for you.
I've definitely sensed a greater awareness among the public. And I agree with you that I think most people don't have any real disagreements with the fact that glaciers are shrinking around the world, right? The photographic evidence is undeniable. The reason that I spent some time there toward the end explaining why the melting of the glaciers now is different than the melting in the past is because that question still comes up pretty often. And it's usually pitched as, well, the climate's always been changing, right? Isn't this just part of natural change? Or at least that last part is implied, I think, in the statement. And that's why I think it's really important that people understand those plots that I showed of temperature and CO2 going back into the geologic past, because when you really understand what's happening there and sort of the limits on the highs and lows of both the temperature and the CO2, it's pretty clear that what's happening now is out of bounds, right? Truly, it's not something that we see in the geologic record in at least the past million years. So when people say the climate is always changing, that implies that they understand the science enough to know that there have been glacial, interglacial periods. And my hope is that they can take the next logical step forward to understand why the natural climate changes are telling us why the present situation is not like that, why it's due to human activities.
Thank you. And our last question, Professor Jeff Tolhurst from Columbia College asked,
Hi, Jeff.
He's asking, what direction will you or the YNP geological research take with the loss of glacial studies? In other words, when the glaciers disappear, what's your next job? I think that's his question. And he also asks about suggestions on what students who want to work on climate change and geosciences should focus in on school, what skills or content. So kind of like what's going to happen to you and what should students study regarding climate change geosciences in school? What skills and content should they focus on learning?
Okay. Well, the first part of that, it makes me sad to think about what I would do when the glaciers retreat. Honestly, I can't say I've really explored that mental space very much. I'll still have work to do if I'm still the geologist. There will be plenty of geology work to do in Yosemite with understanding the granite and the landscapes and helping the park deal with rock falls. Personally, I've really, really enjoyed doing these glacier surveys, in large part because, as I mentioned, it really makes me feel connected with people that have worked on the glaciers in the past. So I will feel sad, I think, when that's not possible anymore. In terms of students preparing themselves to study climate change, I think it's important to take coursework about climate change. I think it's important to take coursework about Earth's history. My sense is that understanding is really important for understanding our modern times and helping other people put this all in context and understand our modern times. In addition to that, from the technical side of things, a lot of what I showed you with the volume reconstruction was computer-based analyses of topographic data, remote sensing data, satellite imagery, LiDAR data. I think those are all really good tools to have in your toolkit as an up-and-coming geoscientist, because the power of those sort of computer-based analyses is amazing. And that coupled with field work, which is always an important part of all this, I think that's going to lead to a successful career in geology.
All right, well, I wanted to thank everyone for all the great questions that people have been asking. Thank you very much, Dr. Greg Stock, for the fascinating talk. I really loved all the pictures that you have there as well. In general, I sometimes feel like people take too many pictures, but this is an exception. I think that these pictures are really great, all the historical and all the pictures that you have nowadays. And I did want to point out that in the notes underneath in the YouTube page, there is a link to a video. So there's a short video showing people actually hiking around on the glaciers. So I encourage people to go and take a look at that. And I think I wanted to thank everybody again for a great talk. Thanks for coming. And I hope that we see you again at the end of the month for our next talk on April 22nd for Earth Day at the museum, and maybe in a week for Science Night at the museum. So have a great night, everyone.